Welcome to Mathtopia Academy. My name is Holly, and I will show you how to solve problems 26 through 30 on the Sprint Round from the 2026 MathCounts. The equation 6x squared plus 11x minus 10 equals 0 has two solutions, x equals a and x equals b. What is the value of a plus b minus ab? Express your answer as a common fraction. Okay, so this equation right here is a quadratic equation since it has an x squared term. And if we were to factor this, knowing that the roots or solutions are x equals a and x equals b, we would have x minus a times x minus b, where a and b are the roots of this equation. And then we're also going to have a constant term. This is not a root. I'm just going to call it capital C, and that would be basically this 6 right here. And this equation is just the factored form of 6x squared plus 11x minus 10. And since this equation is factored out, or expanded out, we're also going to expand this equation. So we have c times x squared minus ax minus bx plus ab. And then expanding that farther, we have cx squared minus c times a plus b x plus c ab. And again, this equation is the same as this equation. So to figure out what c and a plus b and ab are, we can compare each of these terms, our x squared term, our x term, and then our constant, to the corresponding terms in our original equation. So starting with our x squared term, we have cx squared, which is the same as 6x squared. So cx squared equals 6x squared. We know that c is going to equal 6. And then for our x term, we have negative c times a plus bx is the same as 11x. So negative c times a plus b x equals 11x. We know that c is 6, so negative 6 times a plus b equals 11. And we have a plus b equals negative 11 over 6. And finally, we're going to compare our constant term, CAB, to negative 10. These are equal, so CAB equals negative 10. We know that C is 6, so 6AB equals negative 10, and AB is negative 10 over 6. Now, this is all the information we need to solve this problem because it doesn't actually ask for what the roots A and B are. It just asks for a plus b minus ab. And we do have a plus b, which is negative 11 over 6, and ab, which is negative 10 over 6. So putting this together, a plus b is negative 11 over 6, and then minus ab minus negative 10 over 6, so that's plus 10 over 6, equals negative 1/6. And that is our answer. Audie the frog wants to hop from the point 1, 1 to the point 11, 11. On each hop, Audie can either jump 1 unit upward or 1 unit to the right, but only to a location having at least one odd coordinate. How many different paths can Audie take to reach his destination? To start, I just have a blank piece of graph paper to help us illustrate this scenario more easily. We know that Audie starts at the point 1, 1 and can either move 1 unit upward or 1 unit right. But wherever he lands, it has to be a point with at least one odd coordinate. So let's figure out what that means. Well, Audie starts at the point 1, 1, which is an odd coordinate and an odd coordinate. And I'm just using O's to represent odds and e's to represent evens. So if Audie jumps 1 up, that's affecting the y-coordinate. So now he's at an odd point and an even coordinate. And just to illustrate that, that would be him going up 1 like this to the point 1, 2, and we can see that that's an odd number and an even number. This is just for generalizations, so this is if he goes up 1. And then if he can either go up or right. So let's just say that he goes right. That affects the x-coordinate, so now he's at 1 plus an odd, which is an even, followed by an even, and we can see that if he goes right and ends at the point 2, 2. However, this doesn't work because 2, 2 is 2 even coordinates, and we need at least 1 odd. So he cannot go right after going up. That means that he has to go up again, which would make him land at an odd point and an even plus 1, which is an odd. And on the graph, that would be like him going from the point 1, 2 to 1, 3. And this works because it's 2 odd coordinates. So we see that no matter what Audie does, he can't go up and then right. This does not work. Instead, he has to go up and then up again. And I'm just using U's to represent ups and R's to represent rights. And we could do the same thing here like we did with the y-coordinate going up with the x-coordinate. So for example, Audie cannot go 1 right and then 1 up. This doesn't work. He'll land at an even coordinate and an even coordinate. Instead, he has to go 1 right and then another right. So Audie can either move up and then up or right and then right. So this right here is good. This is what he can do. So now for the total amount of ups and rights that Audie has to move, he has to end up moving up 10 times. So up 10 times, and then right 10 times as well. And then we want to find out the number of paths that he can make by eventually landing up 10 and right 10. And our restriction is that whenever he moves up, he has to move up again, and whenever he moves right, he has to move right again. So this is basically like saying that he has to move up 2 times 5 times. I know that can be a bit confusing. Let's just say that a capital U is the same thing as going up, and then a capital R is the same thing as going right and then right. So him going up 10 times is the same as him going up twice, so capital U, 5 times. And then that's the same thing as him going right twice, so capital R, 5 times. So now to count the total number of paths, this just becomes how many ways that we can arrange 5 uppercase U's, so 5 times that he moves up twice, and 5 uppercase R's, so 5 times moving right twice. And then to find the total number of paths, we just need to find the total amount of combinations of this, which is 10 factorial for the 10 U's and R's, divided by 5 factorial for the 5 U's and 5 factorial for the 5 R's. And just doing this without a calculator, this is 10 times 9 times 8 times 7 times 6, divided by 5 times 4 times 3 times 2. And then we can cancel out a few things. And we are left with our answer, which is 252. I'll just write this here to make it easier. So there are 252 possible paths. In the drawing below, equilateral triangles are erected on the outside of a square, with shared edges of the square in each triangle coinciding exactly. The total area of the shaded region shown is 10 root 3 units squared. What is the total unshaded area inside ABCD? Okay, so I'm just going to start by enlarging this image so that it's easier to draw on. And since ABCD is a square, we can call this side length S, so this side length is also S, and the area of ABCD is S squared. But we don't want the total area of ABCD, we want the total unshaded area. So we're going to subtract the shaded area, which is made up of the equilateral triangles, which is 100 root 3. So our answer is ultimately going to be S squared minus 100 root 3, so we have to find S. In order to do this, if we cut the square in half, we've actually created a new triangle, which I'll draw out to the side. And this side length is S, this side length is S. This is our 90-degree angle, making each of these angles 45 degrees. So we have a special right triangle, a 45, 45, 90 triangle, which means that the hypotenuse is S root 2. So this length is also S root 2. So basically, in order to find S, we just need to find this length right here, which is made up of the altitude of one of our smaller triangles, plus the side length of this square, plus the altitude of one of these smaller triangles again. So to start, let's just take a look at one of the smaller triangles. I'm going to draw it out to the side again to make it easier to see. We have our altitude, which is what we're ultimately trying to find. And since we know that it is equilateral and therefore equiangular, this is 60 degrees and this is 30 degrees. So we have another special right triangle, a 30, 60, 90. So if this side length is S, then this will be x root 3, and this will be 2x. And the total area of this triangle is going to be x squared root 3, because we have, x squared root 3, because we have 1/2 times the length of the base times the height. Now, if the total shaded area is 100 root 3 units, that means that each triangle is going to be 1/4 of that amount. So 100 root 3 divided by 4 is 25 root 3. So 25 root 3 is going to be the area of one of the smaller shaded triangles. So now solving for x, we get that x equals 5. So x equals 5, the altitude is 5 root 3, and then the total side length is going to equal 2 times 5, or 10. So now drawing that in on our diagram, we have 5 root 3. I can draw that down here too. And then in order to find the side length of our square, which is going to be the other part that we need, we know that this length is 5 and this length is 5, making this length 10, since this is all part of the same square. So this length is also 10. Okay, so now we have all of the components we need to find s root 2. So s root 2 equals 5 root 3, which is our altitude, plus 10 plus 5 root 3. So s equals 10 root 3 plus 10 divided by root 2. But remember, in our final answer, we have s squared right here. So we're just going to square both sides to find that. So s squared equals 300 plus 200 root 3 plus 100 divided by 2. I just expanded all of that. And s squared equals 200 plus 100 root 3. So all we need to do now is to plug this answer, what we got for s squared, back into here. And we're subtracting 100 root 3 because we're subtracting the total shaded area in order to find the unshaded area. So we have 200 plus 100 root 3 minus 100 root 3. The 100 root 3's cancel out, and we are left with our final answer, which is 200. A digit d in a positive integer is dominant if at least half of the digits in the integer are the digit d. How many positive integers less than or equal to 2026 have at least one dominant digit? To start, we know that we're working with digits here, so we can separate this problem by looking at 4 different cases. The case with 1 digit, 2 digits, 3 digits, and 4 digits. After that, we can find within each of those 4 groups how many integers are dominant, and then we can add our results. So first, looking at our 1-digit integers, these would be the numbers 1 through 9. So 9 total integers within this range. And in order for a 1-digit number to be dominant, it needs to have at least one dominant digit. And since a 1-digit number only has 1 digit, all of the 1-digit numbers are going to be dominant. So there's 9 dominant 1-digit integers. Next, looking at our case with 2 digits, these would be the numbers 10 through 99, which is 90 total integers. And in order for a 2-digit integer to be dominant, it needs to have at least one dominant digit or 2 dominant digits. So that means that it has 1 digit that is the same, so that number can come in the form of AB, where A and B are different digits, or 2 digits that are the same, that would come in the form of AA. And since all 2-digit integers come in this form, that means that every 2-digit integer is dominant. So that means we have 90 2-digit dominant integers. Next, we look at our case with 3 digits, which would be our integers 100 through 999, or 900 total integers. In order for a 3-digit integer to be dominant, it needs to either have 2 dominant digits, so 2 digits that are the same, or 3 dominant digits, or 3 digits that are the same. And this number could come in the form of AAB, where A and B are different digits, or it could be any combination of AAB, so ABA or BAA. And then it could also have 3 of the same digits, so that would be in the form of AAA, where A is just the same digit. And these are all of our possibilities for a 3-digit dominant integer. And we could count all of these scenarios, except it gets a little tricky because our first digit, we know, can't be 0 because a 3-digit number can't start with the digit 0. So what's actually easier is if we do complementary counting. So the difference between a number having 2 digits that are the same or 3 digits that are the same is having a 3-digit integer with all different digits. So that would be in the form of A, B, and C, where A, B, and C are all different digits. And since we know that there is a total of 900 3-digit integers, we can take how many ever 3-digit integers with all different digits that there are and subtract that from our total of 900 to find the amount of 3-digit dominant integers. So counting this is much easier because we have 9 total options for our first digit, because it can be any of the 10 digits except 0, because we can't start with 0. And then B can be any of the 10 digits except what we chose for A, so 9 options. And then C can be any of the 10 digits except what we chose for A and B, so there's 8 total options. And this equals 648. So there's 648 3-digit integers that are not dominant. So in order to find the total number of dominant 3-digit integers, we take 900 and subtract 648 to get 252. Okay, next we can look at our scenario with 4 digits, and we can further break this up into 2 cases. The first case is the numbers 1,000 through 1,999, so 1,000 total integers right here. Or we can look at our case with 2,000 to 2,026, so 27 integers here. Looking at our first case, we can use the same complementary counting that we use for our 3-digit numbers. So if we have our 4-digit number, we know that the first digit, the thousands place, has to be 1, since we're looking at the digits 1,000 through 1,999. And then in order to make all of the following digits different, we have 9 total options for our hundreds place, because we can choose any of the 10 digits except 1, which is right here. And then for our tens place, we can choose any of the 10 digits except what we chose for our thousandths place and hundredths place, so 8 total options, which means there's 7 total options for a different ones place digit. 9 times 8 times 7 is 504, so there's 504 integers that are not dominant between 1,000 and 1,999. So there's 1,000 minus 504, which is 496 total dominant integers within this range. And next, looking at our case from 2000 to 2026, we know that our first digit has to be 2, our second digit has to be 0, and now our digit in the tens place can either be 0, 1, or 2 to fit this range, but since we're counting all the integers that are not dominant, it can't be the digit 0 because we've already used that here, and it can't be the digit 2 because we've already used that here. So this digit has to be 1, which means the ones digit can be any of the 10 digits except 2, 0, or 1. So there's 7 total options to make a 4-digit integer within this range that is not dominant. So to find the total number of dominant integers, we take our total, which is 27, and then we subtract 7 to get 20 dominant integers between 2000 and 2026 inclusive. Now we have all of our totals, so we know the total number of 1-digit dominant integers, 2-digit dominant integers, 3-digit, and 4-digit within this range. So we can add them up, so 9 plus 90 plus 252 plus 496 plus 20 to get a total of 867 dominant integers within our range. If the real number x satisfies the equation, the square root of x squared plus the square root of x plus the square root of x squared minus the square root of x equals 2, what is the value of 8x? Express your answer in simplest radical form. So we're given an equation, which is this, and if we can solve for x, then we can get 8x by just multiplying that value by 8. So rewriting our equation, we have the square root of x squared plus the square root of x plus the square root of x squared minus the square root of x equals 2. To get rid of the radicals, we can square both sides. So 2 squared. And just expanding this out, we get this term squared, which is x squared plus the square root of x, plus 2 times both of these terms multiplied. So 2 times the square root, we can put this all under one big radical since we're multiplying 2 radicals together. So x squared plus the square root of x times x squared minus the square root of x, and then add this term squared. So plus x squared minus the square root of x And all of this equals 2 squared, which is 4. Now we can combine some like terms, so we have the x squareds, which is going to give us 2x squared, and then our square root of x's cancel out, and we are left with 2 times this. Now what's convenient is that we have x squared plus the square root of x times x squared minus the square root of x, which looks similar to, if I were to write it out on the side, a plus b times a minus b, which is just a squared minus b squared. So using that, we still have the square root, but then we have x squared squared, which is x to the 4th, minus the square root of x squared, which is x. And all of this still equals 4. Now we still have a radical, but we can get rid of it by squaring both sides again. But to make it easier, we can get our radical onto one side of the equation. So 2 times the square root of x to the 4th minus x equals, moving our 2x term to the 2x squared term to the other side, we have 4 minus 2x squared. Now we can square both sides of the equation again. And then we get 4 times x to the 4th minus x equals 16 minus 16x squared plus 4x to the 4th. We can expand out the left side of the equation, so 4x to the 4th minus 4x equals 16 minus 16x squared plus 4x to the 4th. Our 4x to the 4ths cancel out, and then we can rearrange this equation to get a quadratic in standard form. So we have 16x squared, just moving the negative 16x squared to the other side, and then we have minus 4x, and then moving our 16 over, minus 16 equals 0. And I'm just going to move my work over here. We can divide both sides by 4 to make it look a little neater. So we have 4x squared minus x minus 4 equals 0. And to find what x is, we can use the quadratic formula. So x equals 1 plus or minus the square root of negative 1 squared minus 4 times negative 4 all over 2 times 4. So x equals 1 plus or minus the square root of, all of this will be 65 over 8. So we have what x is, but we have two different possibilities for x. X can either be 1 plus the square root of 65 over 8, or 1 minus the square root of 65 over 8. So we have to decide whether we're going to use the plus or the minus. Now it's helpful to look back into our original equation up here. We have the square root of x. And in order to take the square root of a number, it has to be positive. And if we were to use 1 minus the square root of 65 over 8, that would be a negative number. And we can't take the square root of a negative number, so we have to choose our positive option. So x equals 1 plus the square root of 65 over 8. And since we're finding 8x, we can multiply both sides by 8. And we get 1 plus the square root of 65. And this is in simplest radical form, so we're done. I hope you enjoyed these video solutions. As you prepare for your next math competition, make sure to check out these great resources now available on Amazon.